So I want to look at a few more problems dealing with functions. So let's say we have a function f of x is equal to negative 2x plus 10. And we want to know where is f of x equal to 0. So our objections are going to say find the values for which f of x is equal to 0. So this is a little bit different in the fact that we don't have f of a number, and in that case, we're trying to figure out what's the y value when I plug in some number for x. Now we're saying we want this f of x to be equal to 0, and essentially we're looking for x values in this case, not y values. So if we were to plug 0 in for this f of x, now we have an equation that we can solve. So we can solve this by subtracting 10 from both sides. So we have negative 10 is equal to negative 2x. And then we can divide everything by that negative 2. So we're going to get x is equal to positive 5. So that's the value that makes this function equal to 0. So we could also think about this way. Because we've talked about x and y intercepts, we plugged 0 in for f of x, and f of x is just another way of saying y. So this is actually an x-intercept. So I'll say note that. Let's do another one. Suppose we have f of x is equal to x squared minus 5x plus 6, and the directions are the same. Find the values for which f of x is equal to 0. So we're going to set 0 as our f of x, just making that substitution there. And now we have a quadratic that's equal to 0. And to solve a quadratic, remember, you have to have everything on one side, and then you're going to factor. So this guy factors into x minus 3 times x minus 2. And then we can set each factor equal to 0. If I add 3 to both sides, I'm going to get x equals 3. And I'm going to get x equals 2 here when I add 2 to both sides. And once again, this guy is an x-intercept of that function. So let's change it a little bit. Let's change our directions. Let's say we want to find values for which f of x is equal to g of x. And let's look at a couple of examples here. Suppose we have f of x is equal to x squared plus 1. And we have g of x is equal to 3x minus x squared. We want to know where these functions are equal. So all we're going to do is we're going to do a substitution. We're going to set that f of x function, which is x squared plus 1, equal to our g of x function, which is 3x minus x squared. Notice we have an equation that's in terms of just x's. So we need to solve this. And to solve a quadratic, you have to move everything to one side. So I'm going to add x squared to both sides. I'll write this out for you so you can see what's going on. So I have x squared plus x squared is a 2x squared plus 1 is equal to 3x. Then I'm going to subtract 3x from both sides. Now notice I can't combine an x term with an x squared term. So this is just going to be a 2x squared minus 3x plus 1 on the left. And that's equal to 0. So to solve this, we're going to want to factor. So we can go through our factoring algorithm. We talked about the AC method. In this case, our A times C is going to be 2 times 1, which is 2. And then we ask, what can we multiply together to get 2? Well, we can multiply a 1 and a 2, or a negative 1 and a negative 2. Oops. We need them to add up to that -3, so we're going to use that combination. So we're going to do a rewrite. So 2x squared minus x minus 2x plus 1 is equal to 0. Do our factor by grouping. We could pull an x out of the first two terms. We could pull a -1 out of the second two. And the reason we want to pull that -1 out is so that we have a 2x minus 1 in both of those parentheses. Remember, you have to have the same thing in the parentheses. Pull out what they have in common. They have that 2x minus 1 in common. Leftovers are x minus 1. Now, once you have factored a few times, you may be able to see how to get from here to here. So you may not need to write all of this, and that's perfectly fine. Factoring is one of those things that the more you practice it, the better you get at it. So now we're going to set each of those factors equal to 0. So we have 2x is equal to 1. So x is equal to 1/2. And then we have x is equal to 1. So those are the x values for where this function is equal to this function. So graphically, what's going on is that we're looking for intersections. That's what it means when one equation is equal to another equation. So let's graph this one in GeoGebra. So I'm going to say y equals x squared plus 1. And then the second equation was g of x. I'm going to use a y equals again. 3x minus x squared. So if we were to look at that graph, and I'm going to zoom in, and you can do that just by pinching. Do you see how we have an intersection here? And if we touch the graph, GeoGebra is nice because it will tell you, you can use your mouse and you can click on it if you type this in GeoGebra yourself. So you can see that intersection. You see how that x value is 1/2? That's exactly what we found on the other page. And then up here, you see the intersection is that x equals 1, which is the other value that we found here and here. So that's what we're finding. To find those y values, which we're not interested in right now, but if you wanted to, you can plug those back into either function and you'll get the y values. So just for fun, let's do that. So we found x is equal to 1/2, and we want to know, what is that y value? Well, we can plug that 1/2 into either equation, because that's where these two are equal to each other, which means those y values have to be equal to each other. I'm just going to plug it into this one. So 1/2 squared is 1/4 plus 1, and that's going to be 5/4. So that's finding what's called a point of intersection. And that's when x equals 1/2, y equals 5/4, which is exactly what we saw over here for that intersection. 5/4 is the same thing as 1.25. And we'll do the other one for fun as well. We had 1, I believe. Yeah, 1 came out here. So if we plug 1 back into our function, I'm still going to use that. But it does not matter which one. We have 1 squared plus 1, and that's equal to 2. So our point of intersection is the point 1, 2. So that's finding where f of x is equal to g of x. The last thing I want to talk about in this section is something called a piecewise function. So piecewise functions are kind of neat because they are functions that are defined in pieces. So let's look at an example so I can explain what that means. So we have f of x is equal to x squared plus 1, where x is less than 0. And then we have x minus 1, where x is greater than or equal to 0. So when we talk about a piecewise function, notice this function here has two different pieces. We have that piece. Now this piece only works for x values that are less than 0. If we have an x value that's bigger than 0, we can't use that top piece. We would have to use that bottom piece. So let's do some evaluating. So the directions are going to say, how do I want to write this? Find f of x when x equals -1, 0, and then 1. So we are finding f of -1, we are finding f of 0, and then we are finding f of 1. You really have to ask yourself, which piece are you using? So if we're looking at -1, notice our x value is -1. We have to ask where, for which piece, this one or this one, does that -1 fall in the domain? Well, we know -1 is less than 0, so we're using that piece to evaluate. So when we substitute in -1, we're going to get a value of 2. So there's our answer for this. That's our f of -1. So the point that's on the graph has an x-coordinate of -1 and a y-coordinate of 2. If we look at f of 0, we need to ask, which piece does 0 fall in the domain? Is it the first piece or the second piece? And we know that's going to be the second piece because that's for every x value greater than or equal to 0. So then that 0 is going to go in for that x for that last piece. And if we evaluate that, we get a -1. So the point that's on our graph is 0, -1. And then if we look at f of 1, we're once again asking, which piece do we use? Top or bottom? Well, 1 falls in this domain, x is greater than or equal to 0, which means we have to use that piece. And we're going to end up getting 0 there. So then our point that's on the graph is the point 1, 0. So that's how we evaluate piecewise functions.